the temperature drops rapidly. I think we even reach 50 minus, that's what the computer said. But then there is the tropical pause, generally these pauses here, where the temperature does not change with altitude. And then this trend, or the gradient, is reversed. And then it actually gets slightly warmer when you go further up. And go to the mesosphere, it gets a lot colder again. And then it increases. So these layers are then called the inversion layers, where the temperature gradient changes. Since it's inverse gradient, it's an inversion layer. And this is essentially the same, just a bit more what we expect at those heights. This goes up to 10,000 kilometers up here. So it's not to scale, of course, this is 630 kilometers. But you have the mountains here and the airplanes that can fly up to whatever, 15 or maybe 20 kilometers. If you want to get above this atmosphere, and there's a reason for it, because that's also the height where the clouds can extend up. If you go above that, then you need, or you want to go above that, you need some weather balloons, or astronomers have launched balloons or rockets to greater heights. Then in the mesosphere you have meteor showers, and then at about 100 kilometers, this is where this phenomena of the aurora is observed. Well, I think you can't see the aurora from the beginning, but so I think it was once possible actually from that. Yeah, and then of course, if you go up hundreds of kilometers, then you're close to what people consider outer space. So don't turn your sheets around. Don't leave them. What do we know about the atmosphere? What are the constituents? What's in the atmosphere?
Nitrogen, oxygen, other elements, you know. Mainly,
Yes.
mainly nitrogen or oxygen.
Okay, so this is the. Of course, I mean the list that we will look at here is of course a list also that's very relevant to astronomers. And yeah, there may be other elements in there. Of course, if you live close to a factory, you may have all kinds of poisonous gases. But I didn't list them here. But what's important for astronomy, of course, well, for everyone, it's important to have oxygen and nitrogen there. You know approximately what relation? In what percentage? Yeah. Yeah. 80. It's close, right? So 87% oxygen, 21%, let's say, nitrogen. So that gives us 99%. 99% of the atmosphere is oxygen. And it's actually a relative constant ratio, up to 100 kilometers. So it doesn't matter if you take a balloon, you measure, you will always find this ratio up to very high altitude. Then there is ozone. And of course, ozone also, yeah, well, if it's a very, not sure how it's here, but at least in Europe, there's often ozone warning, which you should take serious if you go jogging or run marathons when the weather is really hot in summer. And there's some increased ozone content. But astronomically speaking, it's mainly because it absorbs the UV radiation. And, well, of course, we know that from climatology studies. Right, when you have a hole in the ozone layer up there, then of course a lot of the UV light comes through. This is of course where parts of Australia, for example, suffer from. Simply because, well, especially animals get sunburn. But then the distribution depends very much on the latitude, the season. Well, as I said, it's a maximum concentration around 16 kilometers height. Then of course we have CO2. That's what cars produce CO2. And it's important, it is, of course, I mean, there's not much left here, since this is 99%, but the CO2 is important because it's a very strong absorber, meaning that it absorbs, we see some spectra later, how things get absorbed, but it takes out a lot of the radiation at mid-infrared wavelengths. And that makes it very difficult on the ground. Then we have ions. And those ions are mainly above 60 kilometers. And that is because, well, the sun produces lots of UV photons. And the UV photons from the sun, they bombard the upper layers of the atmosphere, and then they ionize whatever is up there. And because the density is low, these ions they well, remain ionized for hours. They do not immediately recombine. But they remain ionized, and this absorbs at very specific wavelengths. And then finally, there is water vapor. Right? And so if I asked Brown Weisler in the observatory in Columbia, that may be one of the reasons. Because clouds are bad, and there may be, I mean, even if it doesn't really show up as a big cloud, the water content is significant, and so it absorbs a lot of the radiation, and then, yeah, that kills the observation. Now, the water vapor, however, is mostly concentrated below 5 to 10 kilometers, which is actually good. So if we had, well, like Mars has, right? If we had a mountain that's higher than 10 kilometers, that would be a good observing site. But let me show you what's happening here. This is a plot of the atmospheric opacity, or you could say transmission. No, sorry. It's the opacity inverse, it's the inverse transmission. Meaning that if it's 0%, it's perfect. If it's 100% opacity, it means nothing will get you. Right? The window is close to 0, the wall is 100%. So you have generally two cases of absorption. You have bands or wavelengths ranging to total absorption, like here. No light will be observed on the ground through those wavelengths. And you have partial absorption, like in this range here, where on average the transmission is reduced, but you will still be able to see something. It's not perfect. Well, at the visible first, it's perfect. And it's probably not a coincidence that humans have developed eyes that are sensitive to the light that we can see and not to wavelengths that are being absorbed. But yeah, so this is the spectrum we all have to deal with when we do observations from the ground.
Where this little percentage of no visible light is because the albedo, or why? Because I was supposing that the visible light reached the surface totally, but
oh, you mean because why this is not at 0%? It is close to 0, but well, if you would take a, let's say, a very high resolution spectrograph, you would see lots of individual lines from the atmosphere. So even the visible wavelengths, there are lots of individual molecules and ions and elements that absorb. We actually can. I mean, the situation is very good there. It gets worse at longer wavelengths, and we can see how. So this is again the percentage. It's a function of wavelengths, so you can see how it goes down here. And there, you see the different components that contribute to this absorption. So if there is a lot of gray, it means it's bad. So obviously the water vapor is probably the worst thing. Right? And the water vapor absorbs everything, well, onward here of 15 microns almost. Then you have carbon dioxide, CO2, and you can can see, there are very distinct wavelengths. It makes the atmosphere opaque. Oxygen and ozone, as I said before, in the UV, but also some features here. And methane is I know Jorge may like methane. It's a key molecule that you would like to observe in exoplanets. And once you see methane, of course, then it's a good measurement of the composition of the exoplanet atmosphere. The only problem is the light that comes from the exoplanet goes through the atmosphere of the exoplanet, and then it goes through our atmosphere. And it's also methane. And so then to figure out, do I really see methane in the exoplanet? Or is it just because I didn't calibrate the atmosphere of the Earth properly? That's one of the big challenges. So, well, you can see, it's very nasty. And you can also see here that at the visible wavelengths here, a lot of or a significant part of that it doesn't go down to zero is simply from radio scattering. And let me say another thing about the water vapor. This plot here shows the temperature as a function of let's say, the amount of water per cubic meter of air. So how much water can this water vapor contain in a cubic meter of air? Right? If it's a lot more, then it starts raining. And you can see that, of course, if the more air is warm, then it's warm. Here's the temperature, but there can be a lot of air, a lot of water in the air. If you cool it down, then the content is very small. And so if you go up on a high mountain where the temperature is low, then you also have very low water vapor. And it's actually called the reciprocal water vapor. And I always have to practice that word. Reciprocal water vapor. And it's the amount of water essentially in the column. You look in the column and you just integrate along this column. And then you have, if this were all sort of raining out, you could measure it, it's about 1 millimeter of water altogether. But of course, in reality, it's over kilometers dissolved as water vapor in the air. And, okay, so you just have to, don't worry about this equation here, but so the water vapor is simply the integral from where you are to infinity across all the water along the line of sight. And it has an impact immediately.
Sorry, Garan. Which is the units of this zeta in the, yes, is meters or centimeters or millimeters?
Zeta? This says grams.
This is
This is a gram.
This is a G. This is a G.
Grams of water.
Grams.
Grams of water per cubic meter. Okay, so this shows again the transmission now for a longer wavelength. I mean, the optical would be here. So from 70 micrometers up to 1,000 micrometers. This is already the radio, this is the millimeter regime, the far infrared, and the mid-infrared. And the black line here shows you that if you had only 0.1 millimeter of water vapor, you would still have 80% transmission. That's correct. If you had 3 millimeters of water vapor, well, this is the green curve here, well, you have 5% transmission. Forget it. Don't even waste your time. Yeah? Now, of course, these numbers may not mean much to you, but 0.1 is exceptional. I think at the South Pole, where it's really cold, you have something like 0.2 millimeters. So people are planning observatories at the South Pole, and that's one of the reasons. Because it's so cold there, the water vapor content is very small, and it opens up all kinds of windows in wavelength space for observations.
So for this N function and a water, do you measure or calculate that number inside the integral? Yeah.
This is something you can measure.
Okay.
Yeah, maybe supposedly with radio songs. And but of course, people making models of the atmosphere could also calculate it. I think you need the model to then see how it's actually distributed if it's not such a nice smooth curve in reality. But I mean, this is usually we measure it and we assume it's.
Yeah, but how do you measure the water vapor in the atmosphere? How do you measure it?
Oh, you just look at, you know what how the molecules are absorbing, and you measure the for known features, you measure how far these are absorbed. So you make a differential measurement. I mean, let's say you look at the black body, you have some continuum. You just need to look at the absorbed at the light at the absorbed wavelengths and the light at the transmitted wavelengths. And the ratio tells you immediately what the precipitate water vapor is. Now, if you go to dry regions in Chile, where many modern observatories are being built, I think you have something like 0.6 millimeters. It's called the driest place on Earth. I mean, there's a few clouds, but it's warmer than at the South Pole. So you have some, say, 0.5 millimeters, 0.6. I think the green curve is more representative of light. And so we don't have any big telescopes there, apart from the radio, where this doesn't matter. And yeah, so it's very important to go for longer wavelengths to go up at very high mountain.
But, so I have this question, why do we don't build more telescopes on the Arctic or the Antarctic? If it's so devoid of water,
Yeah.
which is the main limitation to the telescope?
Cost and convenience.
So
I
far,
mean, not the
so
South.
cold.
Yeah, well, for you it's closer than for and I mean, it's you should look at the logistics of the South Pole operation. Right? There is the human factor. Maybe it's a good training site for people who plan to fly to Mars. But I mean, it's half a year dark. I mean, the observations are usually done during the winter. Right? It's only one night, but it's a long night. And then, I mean, the human factor is important. So I mean, being surrounded by darkness for half a year and just some crazy colleagues, it's difficult. Operating there is also difficult. I mean, you have the great temperatures, low temperatures. I mean, I give you one simple example, right? I think it's going to tell. You have to work outside. You take a drill, machine, with a power cord, and you have 2 minutes to make to drill your hole. And you have to run, because otherwise the cord gets frozen and you'll never get it back in. Yeah? So this is just one example. I mean, from everything else, restrooms, it's expensive to ship all the equipment here. It's cheaper than to space, but it's very expensive. And then you don't have a perfect flat or solid surface. Because the bigger you make the telescope, the more weight there is, and it sinks into the permanent ice. So does your hotel, if you build one, right? After 10 years, it's under the snow or the ice. So there are problems.
Excuse me, teacher. What about a kind of robotic telescope? Something like that.
Yeah. It's well, where do you put it? Where do you put? I mean, there are robotic telescopes all around the world that simply save the cost for the people operating, right? Because you don't have to send someone. The problem is they're not foolproof. The reason why space astronomy is so expensive is that you have redundant mechanisms for everything. You have everything tested for years before it gets launched. For the robotic telescopes, you just put a motor there and you assume it's working. Now, if you ship the robotic telescope that was built in that way to the South Pole, I can guarantee that it will fail during the first night. Something will break and it was not considered properly, and then you need people to repair it. And so you don't have, or you make it like space, and then you have your observatory at the South Pole, and it costs $5 billion, and who's going to pay for it? Space has at least the advantage that you can excite the public. You say, oh, that's a space mission, and we send astronauts there, and politicians like the idea, and South Pole is too far away. So to spend a lot of money.
But I know about a few projects to establish robotic telescopes in the South Pole. In fact, I was in Argentina last year, and my advisor there is working on a project to install a little telescope in the Argentina part of the
Yeah, no, that works. Good point. But they're small telescopes.
Yes.
This is proven technology.
Yes.
Right? But of course, the idea would be that you move the 8-meter telescope from somewhere here, maybe Hawaii, to the South Pole, and then the problem starts.
Yeah.
There was another question.
Yes.
This concept of the telescope in South Pole, maybe it would have only the south hemisphere in the sky.
That's another. Yes, that's another good reason.
You lose the half of the sky.
Yeah. And it's important also that, well, actually the southern part of the sky is the better one.
So we are closer to this part.
Yeah, well, you can look at it. But, I mean, the big ALMA, for example, is on the southern hemisphere. And so many survey projects. I mean, nowadays, you have the big discoveries by combining different wavelengths. Okay? Radio observation, if you combine them with Hubble data and so on, and by looking at all the wavelengths, this is where you find something new about objects. And that, of course, requires that you can, in order to be able to combine your radio data, or your submillimeter data with your optical data, well, you need to have, of course, the same objects, same hemisphere. That was one of the reasons, actually, why ESO said, well, the ELT has to be in the cloud, because we have invested lots of money in ALMA and in the VLT. We have all the data. If we now start on the northern hemisphere, then we have to start from scratch, building up databases. Okay, so this is a NASA cartoon that should show that, well, in the visible, obviously, you can do it from a mountaintop. But if you go to infrared, you need a higher mountain, or you say an airplane, or you go to space, maybe a balloon. The radio is nice, right? The radio is on the ground. And, well, we know that the atmosphere is transparent for radio waves. Right? We know that every time we turn on the radio. And, but then if you go to the UV X-rays, that's actually quite fortunate that the atmospheres will take the X-rays and gamma rays. But that means you really have to launch instead. There's one example for an infrared observatory, SOFIA, the Stratospheric Observatory for Infrared Astronomy, where they have taken an old Boeing 747, cut a hole here in the back, with a door that slides off, put in a 2.5-meter telescope. And so you fly at, I'm not even sure, 14 kilometers, 15 kilometers high. And then you fly around, take off in currently California or maybe Hawaii, and then you fly around. And of course, in this case, it's easy to select your objects. You tell the pilot to turn around. And yeah, absorption, but the atmosphere is also emitting. And there are two types of emission. There is the fluorescent emission and the thermal emission. I already mentioned the fluorescent emission when we talked about ions in the atmosphere, ions in the ionosphere, essentially. So you have the UV photon from the sun ionizing atoms in the atmosphere, in the upper layers. They recombine, not very fast, so the recombination takes time. Now, of course, that problem goes away to some extent during the night. Because, well, I said the UV photons come from the sun, right? And you observe during the night because there is no sun. But since it takes a couple of hours for the ions to recombine, you will have a much stronger fluorescent background in the early part of the night when you're at the observatory than in the later part of the night. Actually, it's quite nice. So they produce these ions produce both continuum emission and line emission, but altogether it's called air glow. So that's sort of the air, sort of the sky is not dark. It glows slightly and mostly at short wavelengths. And then there's the thermal emission. We just assume that the atmosphere emits like a black or a gray body. And I think Elena will get back to black body emission in her lecture later this week. So the intensity is simply black body function times the opacity of the atmosphere times a factor here, 1 over cosine theta. And anyone has an idea what this stands for? So what's theta?
The lambda refraction.
No, not quite. This is a simple, very simple geometry which you want to be here. Right. It's simply the Venus angle. Because what counts here is, of course, the more atmosphere you see, the more emission you see. If you look up through at Zenith, you only look through one atmosphere. If you look close to the horizon, right, the length through the atmosphere becomes a lot longer. And
Plane parallel atmosphere. Plane parallel.
okay, and just to show you, I thought I'll calculate some numbers for you. These are near infrared wavelengths here. 1 micron, 3 microns, 4 microns. I'm not sure why I listed that twice. But this is the magnitude per square arc second. I think you're familiar with magnitudes. The magnitude per square arc second at the telescope. So at 1 micron, the thermal emission is fairly small, only 16 magnitude.
What does IDF mean?
Oh, sorry, that was measured with the infrared telescope facility which belongs to NASA on Mauna Kea in Hawaii. But you can ignore that. The main point is here that the thermal emission gets much stronger when you go to longer wavelengths. In fact, when you observe at 4 microns, you can see that the sky brightness is brighter than the magnitude of Vega, which is defined as 0 magnitude. Right? That's like, if you, because of that background, because the atmosphere radiates at longer wavelengths, this is almost like observing during the day. Right? This is, mid-infrared observations are like daytime optical observations. The sky is so bright, brighter than the stars. And so this is, of course, you can still do it, but you have to have a way to subtract the background, to calibrate that out. Right? And we can just compare here. This is the intensity. I hope the units agree with what William said this earlier today. but the intensity is a function of wavelengths. Here for the near-infrared bands, JHK, so it's 1.2, 1.6, 2.2 micrometers. And then you have the thermal emission here. And you can, I mean, this one, you should be able to recognize the shape of a black body. And so this is really, for this case, an effective temperature of about 230 Kelvin, with relatively small emissivity, but it dominates the background entirely in longer wavelengths.
Sorry, do you know that effective temperature is just an average, or?
It's, well, yeah, I mean, you could calculate it and measure it, but you could, I mean, there are various ways to do it, but you could also just observe the different wave bands and assume it's a black body infinity. Okay, and this was just, I mean, you will find in the lecture a couple of times things like that are in brackets or are labeled side notes. So this is more as a background information for you that you might ignore or look up if it's important. It's just to understand the rest better. This one is additional information just to show you how complex things are. If you would take a spectrum, now it's radiance, but it doesn't really, it doesn't actually matter. Just say that's the brightness of the background as a function of wavelengths. And here you see the individual components from the moon, which is always what can be a problem on the sky when we observe background from other stars, which is faint. So diagonal light, telescope emission, lower atmosphere, airflow, so this is the fluorescent emission. And then if you put this all together, I mean, you have a very complex structure over here. And you have no astronomical source in there yet. So you have to calibrate for that, of course. You have to subtract that out in order, before you can publish the spectrum of your galaxy. Okay, and then we have a few more aspects. There is the atmospheric refraction, and I think most people know about it. Who has a small telescope, or ever looked through it, or operated it? You do? You never told me that.
Yeah. The left telescope in Boulder.
So okay. So what's happening is we're here. We look at the star here. The star is here. Now, when light from the star comes to the atmosphere at well, not at zenith, right? We're here, we said. So zenith would be here, straight up. We don't look at the star here, we look at the star over there. So the light gets here, but because the atmosphere has a refractive index that's different from 1.0. Right? 1.0 would be vacuum. So if we were all the Earth, if we would do this on the moon, let's say, without an atmosphere, this would not be an effect. But since we have an atmosphere that's getting denser and denser as we get closer to the surface of the Earth, the light is spent actually here. So there is an angle between here and here. Of course, this is idealizing it. So we just have an atmosphere that consists of 5 layers. In reality, this is a smooth gradient, but I think you get the idea. So the light, it's like, assume this is like a lake, right? The light travels in here, but then the light will be bent, and the ray is under a different angle, right? That's why it's difficult to whatever, catch fish in your swimming pool. And so the light gets bent, so it's a different angle here, and here, and here. And then finally, this is the direction where it reaches us. And if we sit here and look up on the sky, we see this direction. And this direction, of course, follows, seen from here, follows the dotted line. Right? So the star appears to be here, while in reality it's here. And this is highly nonlinear because of this tangent's theta function. So the refraction R, meaning the angle here, the offset between the true and the apparent source position on the sky, since it's multiplied with that factor, it increases, the refraction increases dramatically with large angles. So you can see here in arc minutes, or actually it's so small that it's hardly noticeable here. If you just look at 10 degrees in distance, then you would not, I think, at least with a small telescope with large field of view, you always see your source. It may not be exactly where you expected it. But when you look at something at the horizon, well, it can be 50 arc minutes, almost 1 degree. Right? So larger than this effect can be larger than the diameter of the full moon. And yeah, this is of course important to know about because big telescopes usually have small fields of view. So if you don't know about this and you point your telescope, you will not see your source because it's somewhere else. But the good thing is that, of course, most telescopes you know about this. This is a very simple mathematical form. So you tell your telescope computer and it knows, okay, I go to 60 degrees zenith distance. So actually I have to go to whatever, 61 or so in order to make it. Okay? So this is the atmospheric refraction. It's a large effect, but it's easy to take out. However, note that the refractive index of the air, like the refractive index of most materials, whether it's glass or some crystal or liquids or gases, is not constant with wavelengths, but it changes with wavelengths. Meaning that this effect is wavelengths dependent. So depending on your observing wavelengths, it may be closer here or over here, and it's a small effect. And the effect is let's say the effect is tiny. If you have a backyard telescope, you shouldn't worry about this. But what it does, and this is shown here, so because it's wavelengths dependent, if you observe at zenith, the red light and the green light and the blue light of your star overlap. They are focused on the same spot. If you go to higher zenith angles, because of this dispersion of the atmosphere, you will see that the red light is actually at a different position than the green and the blue one. And I'm mentioning this here, although it may for most telescopes not be relevant, but if you go to for the next generation of large telescopes, bigger than 10 meters, this will be a problem. In the sense that the sources will be really elevated, like a rainbow, much larger than the resolution or the size of the diffraction limited size of the star. And astrometry is becoming a very, I'm always surprised because astrometry, I mean, just to record and study the positions of objects on the sky, whereas it was a big topic some 50 years ago, and it still is, and becomes more and more important because with proper motions, Elena will actually discuss that in her public talk on Tuesday next week when she talks about the galactic center, measuring the positions and even how they change with time tells you about the dynamics of the system. So you can look at the star cluster, you observe it now, you observe it again in 2 years, and then you may have seen the stars move. And from that motion, you know something about the gravitational potential in the cluster. You know how much mass there is. And for example, and there are many more cases where you really would like to know exactly the position of problem is that the stars are far away and they move a really tiny, tiny, tiny bit. So when we say tiny, I mean something like 50 micro arc seconds. An arc second, that's what you get through the atmosphere, how big the regular star looks like. If you use the Hubble Space Telescope, you may get to 50 milliarc seconds. But now we talk about knowing about the source position, a factor 1,000 better, 50 micro arc seconds. And then all these effects become very, very important. If you don't know the spectrum of your source, if you don't calibrate that out, and actually here's a challenge for you. It's not part of the test, but I say I promise that Jorge will add an extra point to the grade if you tell me tomorrow how this could be compensated for. If you have this effect, you have an idea. Oops, this effect is a problem, as I said, but people are working on technical solutions. If you know how to do that, let me know.
With or without optics?
With optics, but whatever. Whatever. This is,
So I have a question. So you will
get no extra point.
you will need the spectral distribution of the source in order to do command. So in order to do astrometry, you will need the spectrum.
The problem is that in principle, okay, in principle, you could have the rainbow, and you could look at the centroid. Yeah? And if you would always look at the star cluster at the same Venus angle, it doesn't matter. But if you track the objects on the sky over the night, the zenith angle and the air mass will change, and so does the dispersion. And if you have objects of different spectral type, say you look at the cluster that has some red giants and some white dwarfs and whatever, that already have a different centroid, they move them relative with respect to each other, right? And then what you think is proper motion, oh, there is a whatever big black hole there because I see the stars move, is only an optical effect. Okay. But on the other hand, I mean, if you do if you think you want to do a PhD in 5 years, working on some Gaia improvement of Gaia data, well, Gaia will then be up and running, and these are really some kind of questions that will be state-of-the-art astronomy then. But these are problems. Actually, we have a big program to solve that. So the Dutch astronomy program is actually spending $2 million to find a device to do that for an imager on the yield.
Will you be giving those $2 million to the student who answers your question?
No, we know in principle how to do it. But there's also some money needed to implement it.
He explained the y-axis units, which is the y-axis.
Oh, sorry, yeah, maybe that plot is too complicated here. There will be no exam test on this plot, but okay. I'll try it. So ESCO learn on Thursday. Lambda over d, that's essentially the diffraction unit of the telescope. That's how small your source can get. Right? I said before that there's a star on the infinite distance is like a mathematical delta function. But then when you image it with your telescope, you will always end up with some extended block. No matter what you do. However, that block gets smaller and smaller if you use bigger telescopes, right? So lambda over d, if d gets bigger, that factor gets smaller. So and lambda, well, that's the wavelengths. Okay, so let's say you have this telescope here. What this plot shows is the image size is essentially if you would measure from here to here, right, your image elongation. And how it increases with shorter wavelengths. Right? We said this is due to diffractive index as a function of wavelengths. And well, we also know blue light is refracted more than red light. So at shorter wavelengths, the effect increases. But the main point to take away from this plot, just take one curve, right? This is just the difference seen at distances. Let's look at 50 degrees. So we look at the star over there at 1 micrometer wavelengths. And then we can see here that the size of the rainbow here is 100 times, right, roughly 100 times the size of what you would get without the dispersion.
Yeah, 100 meters per second.
It's 100, maybe it is, yes, with 100 meters. So if you take a 1 meter telescope, that effect goes away completely. Right, so you just have to divide, to multiply that with 100. So if you have a 1 meter telescope, you will not see anything. If you take a 100 meter telescope, in one dimension, the source has the same size as the source, only that, well, in the other dimension, of course, perpendicular to the dispersion. You wouldn't see anything. We know that as well. Okay, so much about refraction, emission. Do you have any questions so far?
Let's do a quick test.
You mean, let's say this is all your background. How do you take it out? Yeah. Well, the best thing. Okay. I will get actually back to that later in this course, but the best thing you can do, you don't know all that. And of course, people have models. I mean, there are many people working on radiation transfer models. We'll not talk about this today for the atmosphere. And they're actually quite good now. They're actually sometimes better than some of the calibration observations. So it's getting there. People really understand the physics of the atmosphere. But the easiest thing you can do is you look at the object, say your object, this is the bright object, it's the lamp here. And I observe it, the atmosphere is in between. And I get both. I get the spectrum of the lamp, and I get the spectrum of the atmosphere in between. But the atmosphere is in this room everywhere. So I look at the lamp, and I look next to it, and I subtract the two, or divide. Right? So I essentially compare a spectrum of atmosphere plus object to another observation of atmosphere only. Right? And that's the simplest way of sky subtraction. The problem with that is that you can't do it at the same time. You have to do it afterwards. First you integrate there, and because the object is usually fainter than the lamp here, you integrate for a long time. Half an hour. And then you go to another position on the sky. But in this half hour, maybe the atmosphere has changed. The problem is, the atmosphere is not constant in time. So then you subtract the two. In the ideal case, you can subtract out the atmosphere completely. But because, well, it's later during the night, well, we said before, say, for fluorescent emission, it changes as the ions recombine. So some of the signatures will change with time. And so it's difficult to find the right calibration to figure out how often do you have to go back and forth between your object and the sky. And yeah, that's the art of observational astronomy, to find out what is the best calibration strategy for the data. So, but the simple thing is go back and forth between the object and the position on the sky, which is close to the object. It's also, if you go far away, and far doesn't mean 20 degrees, far is already 1 arc-minute. If you go far away, the atmosphere may already be very different from your actual source location. So you want to go only a tiny little bit away. But of course, if you have a big galaxy, that's not working, because then if you have a galaxy that's 30 arc-minutes, and you go only 1 arc-minute away, then you subtract maybe the outer parts of the galaxy from the central part of the galaxy. And then, so you subtract out features of itself. That's not working. So it's challenging.
Can you use these artificial stars, these lasers or other sources of light that you know is better?
No. No, okay. It's a definite no. Because there are, well, we'll see later when we talk about adaptive optics. There are 2 ways people produce artificial stars. One is with Rayleigh scattering, which is only at 10 kilometers high. These are continuum lasers, essentially, but they only give you the information about the lower 10 kilometers of the atmosphere. So they don't show you what's up there, higher up. Or you can use a resonant scattering of the sodium B line at 90 kilometers high. Then the problem is if you have only monochromatic information and you can't calibrate your spectrum. What you could do, of course, is to send a bright emitter up there. So if you have $1 billion and you don't know what to do with it, you create your artificial source in orbit.
Then you will have the sky full of artificial.
I mean, you could use the space station, for example. It's fairly bright, but it's never where you want it to be.
Yes.
Okay, so
Another question, sorry.
yes, please.
The next question is only that I want to know what is the relation between atmospheric emission and the black body emission. Due to when you talk about 2 types of atmospheric emission, there is something called thermal emission and a periodic equation. In this equation, there are a term, the relation between a black body. So when you study the black body, there are so many things that I don't know, but it's difficult for me. So I want to know the relation of the boundaries between the thermal emission and the black body emission.
Okay, so I'm not sure I understand your question completely. Of course, this is a simplification again, but it usually works. It's a simplification already because if we think about the atmosphere as an onion with different layers, then all of the layers, of course, we know how the temperature will drop, have a different local temperature. So you already integrate over a couple of different. I mean, the nice thing is if you add black bodies, it still looks like a black body, right? So you might have one black body. Okay, so you have the intensity here and the wavelength. So maybe that represents the lower one, and it's warmer. And then you have a fainter one at an upper layer, and then this is even higher up at the atmosphere. And then you also, they're not all contributing the same amount, because as in this formula here, you have the opacity there, and that depends on the density. Right? And of course, the layer on the ground is denser than the one at 50 kilometers high. So that one will contribute even more than that. And so most of the properties are given actually to the layer which is pretty close to the ground. And then we just assume it's black body emission. In reality, of course, it's not, because then you have what's not shown here are all kinds of absorption bands for molecules, right? But this is a higher order effect on top of that. So usually it works quite surprisingly well. You can take you go to the observatory, you hold your thermometer there, and it reads like 10 degrees Celsius, right? Then you assume it's a whatever effective black body of 283 Kelvin, and then you're not so far off. Okay. Okay, turbulence. I realize this is also challenging. And it's not by intention that the most challenging part of the lecture is just before. Okay, let's see first why we worry about this. Right? I wouldn't talk about it if it were not important. This is just a comparison of the same star cluster. In this case, this was Wisconsin, I think, infrared observatory. So this is an image taken at 1.6 micrometers of the star cluster, seen with it. So no correction for atmospheric turbulence. This is what you would get when we point any telescope, let's say, without. On the left one, this is one taken at similar wavelengths. Well, this is at 2.2 microns, but with an adaptive optics system that corrects for the atmospheric turbulence. Same star cluster, same speed. And there are essentially two fundamental aspects that you gain when you get closer, when you overcome the atmospheric turbulence from the sea and get to the diffraction. So there are, what would be the two things that improve? I mean, you just look at me. You should be able to tell me. What differences? I mean, you see some difference. And then you ask, what's the difference that you see?
The size of the point.
So resolution is one thing, right? I mean, we can look here. This one here, I mean, we clearly see two stars. This is one blob, right? So we gain resolution, angular resolution or spatial resolution. But there's another effect here. Any idea? We need to look at that. It's maybe not so obvious in this. Okay, I'm helping because. Can you see that dot here?
Yes.
Okay, I invite everyone from the backward. Okay, so, and there is nothing here. And the point is that if you concentrate the light, then you also have more photons hitting the same area of your detector, or of your CCD, of your photographic plate, whatever. So you gain in sensitivity. You also have what we said before, the background. Thermal background, fluorescent background, whatever. All the background sources we talked about. They're all across They're all across the image. But they're the same here and here. Right? They're per unit area. The background covers the whole sky. It doesn't care about whether we have turbulence or not. It's the same strength here and here for every point. But in this case, the information or the light from the source is concentrated in a much smaller area with respect to the surrounding background than in this case. And so here we can see much fainter sources that would here be beyond the detection. We'll get back to some aspects tomorrow when we talk about signal to noise. But so these are the two main things when you get to the diffraction limit. You gain in sensitivity and you gain in angular resolution. Okay, and there is, yes? No, I was cheating. It's not exactly the same instrument, it's not exactly the same integration time. Yeah, yeah. They're similar, they're comparable, but it's not exactly the same instrument. Yeah. I mean, the same sort of detectors and
About the last picture, the wavelength was taken both are the same or not? No.
Well, yeah, this is 2.2 microns and 1.6 microns.
So
that's for that comparison here.
Okay, we're just comparing resolution.
Yeah.
Okay.
Yeah, I mean, if you would turn off the adaptive optic systems for this one here, you would get a similar result. Okay, so why is that? And I think if you haven't seen how these pictures or what nature does to our ideal points of the star, you should watch here a movie of short exposures. So we said the atmospheric turbulence degrades the image of a point source, but it's not like constant degradation, like a static aberration, like you have an error in your optics. But it's a very dynamic effect, and this is called the scene. And I'll show you. This is a regular. So this is a typical sequence of observations. I'll replay it a couple of times.
That's
So this is really an image of a single star. And it moves around and it has all those structures. And this is simply, well, that's what the atmosphere does to your image. Right? So it does not stay stable. The centroid moves around. The structure of this cloud moves around. And of course, if you now, well, would take a long exposure. Right? As I said, this is a movie of short exposures. Okay, I don't know, maybe this was 1 second altogether for a bright star. But let's say you integrate for half an hour. Of course, then you would get an average of all that. Okay? And the average looks then something like that. Right? All the stars are some blurred blobs. Okay? So that's why we want to understand the atmosphere, why we want to build something that compensates for that. But in order to do that, first let's talk about turbulence. And yeah, I mean, why is the atmosphere, do we know actually that it's turbulent? And yes, we know. This is a sort of a side note. There is one simple quantity that people who study turbulence know very well, the Reynolds number. And the Reynolds number is defined here as the ratio between density, flow velocity, and the characteristic length. Now this is over which we study that. Imagine you have some water flowing through a pipe, then the characteristic length would be the diameter of the pipe, divided by what's called the viscosity. Right? Oil obviously has a higher viscosity than water, and for air, it's very small, or in other terms, the flow velocity times the characteristic length divided by the schematic viscosity. Okay, so if there is a sort of a magic number, 2,200. Don't ask me why. That's sort of the transition point between laminar flows. Right? The laminar flow is what you observe when you're in an airplane and you fly through clouds, then you see the air streaming across the wings. And you better make sure it's laminar, because as soon as it becomes turbulent, you probably have a problem in the plane. But so there is the laminar flow across the wing, or if the Reynolds number is less than it's laminar. If it's larger than that, it's turbulent. And if we include something here for the wind speed, typically an observatory, well, it can be larger than that, but it only makes it worse. Scale lengths of say 15 meters, we get to that point, but then the Reynolds number is 10 to the 6. So in any case, it's turbulent. Right? The air above there is turbulent. And people have been studying the turbulence.
I have a question about the scale length. It's something like the head of the clocks, or is the size of our cell? What is this speaking?
This is ill-defined, but I think I have. Let's see if I have a picture.
I think it's the width of some ladder.
I think I have a. Let me just go back to. This is another approximation. 15 meters. Well, it's not 10 centimeters and it's not a kilometer. So why is it 15? Why is it 15 meters? Because if you have an observatory somewhere in the mountain, that's typical length for separation between big objects. Right? It's the size of your telescope. It may be whatever the size of some trees, something like that. I realize this is not very well justified, but the main point is with 10 to the 6, you're so far above the 2,200 Reynolds number that you can easily use another. If you don't like 15 meters, use 30, you're still turbulent.
But if you have very small values of this quantity, you will have less turbulent processes, right? So if you work, for example, in a desert, instead of a mountain, the mountain process, you have a small value in this part. That's because in Colombia we have deserts, right? To observe, and not mountains.
Yeah, but of course then the problem is that if the wind has no obstruction, it may develop larger wind speeds. So you always lose. Okay, so there was a Russian mathematician, Homogorov, who studied the turbulence carefully. And so we all assume, we meaning people working on systems that correct adaptive optics, or adaptive optics system that correct the turbulence, assume it's always that it's a Homogorov spectrum. We know it's not true, but it's a simple model very more like this. And what it means is that the kinetic energy of large-scale movements is, so your 15 meters sort of, is then gradually transferred to smaller and smaller scales. It's not like you have big turbulence at 15 meters and that's the only thing. You have, that's sort of out of scale, as it's called. And then you have smaller and smaller scale sizes of this turbulence, down to minimum scale lengths. And then at minimum means that if it's below that, the energy is simply dissipated into heat, essentially, by friction. Okay. And what's shown here is essentially the energy of the spectrum as a function of a quantity kappa, which is, or the inverse of kappa is simply the vector that represents these scales. That makes it supposed to be, I mean, yeah, it's hard to give a good explanation, but this is the terminology that people use. And the main point here is that there are two critical values, the sort of inner scale here, that's the smallest scale, right? A few centimeters typically. It doesn't go to infinity, right? We have no turbulence at the micrometer level. So millimeter here, or inverse millimeter, and then here you have a very large outer scale. And in between here, the energy follows the law of the exponent of minus big third. Right? So obviously, at the outer scale, you have more power than the smallest scales. That's it. So the turbulence, essentially, the turbulence is not random, but follows a certain energy or size factor. And this is just illustrated here again. Okay, this is our ground. And, okay, now a couple of sources that contribute to the turbulence. We have winds, lateral winds. We may have convection here. We may have the heat radiation from the ground, heating up the air. And this is what you see on a hot day from the paved road. But you have, of course, also a strong impact of energy input from the sun, from above. And so this altogether creates some turbulence, some outer scale. This is the largest one, to be 50 meters before maybe. And of course, as the turbulence, or if we would just take one big block of the outer scale and we follow it in time, it will break up in smaller units, smaller units, smaller units, oops, down to this minimum inner scale. Okay, and that's the simple picture we have of the turbulence. But if we want to correct things, we have to find some characteristic scale of length. So obviously, this already shows it's a complicated picture. We have big areas of turbulence, we have small ones, but at some point you have to simplify further and define sort of a characteristic scale. So again, what the turbulence actually does, I mean, in principle, if the air were either transparent or had a constant refractive index, it wouldn't matter. But what's happening is that our turbulence mixes the air, and it mixes patches of different temperature. Right? It's not talking about many degrees, but there are tiny differences in temperature between the air here and there. It's never in perfect equilibrium. So you have fluctuations in the temperature, and because of that, you have fluctuations in the density. Simply because the density is a function of the temperature. Okay? Now, if you have fluctuations in the density, you have fluctuations in the refractive index, because the refractive index is a function of the density. And because you have fluctuations in the refractive index, you also have fluctuations in the optical path lengths. So the light that passes from your distant star through the atmosphere. So obviously, this picture we have, is you have a flat wavefront from an object at infinity that goes through the atmosphere. But then that part of the atmosphere has a different optical path length than that part. And so your flat wavefront gets distorted. And that's what's giving you these blurred images. And we can look. This is a bit of math here. I think you know about the statistics and the variance, which is, well, yeah, the statistical quantity, let's compare two values. We look at the refractive index at the point R somewhere. And then there is another, the refractive index at another point, which is offset from R by an amount of rho. So, okay, here is one point, that's n of R, and here is n of R plus rho, because that's the difference between this rho. And so we compute the variance. Of course, we do this for many points. And then we take the difference and the time average. And I mean, this can be measured actually. And then this quantity, that's then the variance between the density fluctuations, the refractive index fluctuations, is called the structure function of the atmosphere. Or you can also call it the Cn squared profile. People talk about Cn squared, that's what's written there. The nicely called the structure constant of the refractive index. Don't worry about this rho to the density third here. And the main point is that this quantity here is the Cn squared. That's something that can be measured. And how exactly this can be measured is I think it's a topic that's too difficult for you. Just the people measure. And what I show you here is actually a measurement of this Cn squared profile. And so again, the mean, obviously you can imagine that if this one is large, that's a relatively large value, that means the variance is large. That means that between 2 points separated by rho, their refractive index differs quite significantly. And if it differs quite significantly, it means it has a very bad effect on your image quality. Right? So you want this to be small. Okay? And I mean, usually you're only worried about the total integrated along the line of sight. Typical value here, don't worry about there will be, okay, I think I can say that. There will be no test asking about the refractive index constant here. This is a difficult subject, and I don't expect you to get this in this crash course immediately, but I thought it's useful to show because the measurements show how this structure function varies with height. So on the x-axis here, you see the height in kilometers above the sun. This was actually measured from Mauna Kea, which is one of the prime observatories on this planet. And here is the Cn squared profile, and here is the height above the observatory. And what you see here is that there are some heaps. And what it means is that most of the turbulence, right, we said before, if this Cn squared profile is large, that means that the density or the temperature, whatever, is very different between 2 points, and that means that it has a very bad effect on your image quality. So if this is high here, that means that a lot of the seeing, a lot of the image blurring will be produced at this point, some 3 kilometers above ground. And then there's another one at high layers, let's say 9 kilometers. With respect to the rest, so actually, if you could compensate for those two, you would already improve your image quite a bit. And that also changes with season. So it's not like your turbulence is always created in the same layer of the atmosphere. So for the same observatory, it varies from day to day. So if you take only the nights with the very best seeing, you can see that this one is completely gone. So apparently there must be some condition in the atmosphere where on average you have some winds at low altitude that give you bad seeing. But if you take the best nights on Mauna Kea, these components are completely gone and you only have some very strong component at 7 kilometers. Maybe some airplane just came by added some turbulence, I don't know. But it's very dynamic, it's changing all the time, and you need to compare, to compensate all of it. So, but the main point you need to take away from this slide is that turbulence is not constant at every layer. It's usually some very specific layers that contribute most of the scene. And the very dominant one in all observatories usually is the ground plane. So that's one of the reasons why people try to build a dome around to shield it from the wind, or to put it actually up on some I mean, many of this, going back to the 15 meters, right? Many of these scale lengths are mostly at the ground level. So if you would build your big telescopes at a on a tower that's 30 meters up, the scene would already be much better. And yeah, but of course that's expensive. The telescope weighs a couple of hundred or 1,000 tons to do it. Maybe the tower is difficult. Okay, but its turbulence occurs at some distinct altitude, and it's changing with time. Okay, now, from turbulence to sea. We've seen these effects before, so this should not be part from that part. Well, one effect we've seen in this little movie that I showed you before. Right? We saw the clouds, the blob moving around. That's called the image motion. And well, one way to look at this is to say we have an object high up there, we have an almost parallel wavefront coming to the atmosphere, and then it goes through the layers of the atmosphere and it gets distorted. So the ideal flat wavefront would give an ideal point source, but now that we have a distorted wavefront, we will see the blurring of the image. Now, that image motion is essentially due to flat parts of this distorted wavefront. So if, let's say, we would look through that part of the wavefront, then we would see the speck that the cloud here. If the wavefront, say, moves by, and the angle or the inclination is a little different, it would move everything just by a small angle, and that means it moves the source around. And that's what's called the tip-tilt motion. And this is also important because many telescopes, especially smaller ones, are equipped with a tip-tilt system. In fact, my pocket camera has an image stabilizer, which essentially does the same, only that it, of course, in that sense, like whatever Canon pocket camera is not supposed to correct for the atmospheric distortion, but just to me shaking while I'm taking a photo. But it's essentially the same principle. It tries to stabilize the image because there is this fundamental zero order component that moves the image around, and simply by tilting and tipping, in this case, parts of the wavefront, other case, whatever, trembling fingers. And then there is the image blurring, which is simply due to the fact that because there are many turbulent cells, the light comes at different angles. And there's a third effect that if more of the light is concentrated, and in this case here, when you would look, right? I mean, imagine you had a telescope here. The telescope would have that size, so it would only see that part of the wavefront. But the moon is moving this way, so the gradient will change all the time. And when the gradient changes, we have this image motion, we have the image blurring with time, and then there's also an effect called scintillation, simply meaning that, of course, if you have more rays being focused here, then this spot appears brighter, and then here again it gets fainter. This is a sort of an effect you should not worry too much, scintillation. But image motion and image blurring is something that will follow us through this course.
noise insulation is not as important, since it's a variation in the brightness sources.
Yes, because in the end, you take a long exposure and you cancel it out. So average is out. Okay, so there is a free parameter that we'll introduce. It's named after an optician, Fried, and that will take a while until you appreciate what it means and that it actually can be useful. So the R naught, this free parameter, often called R naught, that's the turbulence scale over which we consider the wavefront as flat. Okay, so if I go back one slide. Okay, so before, okay, if I have a flat wavefront here from a star as infinity, above the atmosphere, R naught would be huge, right? Below sky. Now we go through the atmosphere, and I can see that first, maybe this part of the wavefront is pretty flat. It certainly isn't flat here. So I could maybe say, well, this size is I consider the wavefront flat, or more precisely, if we want to quantify it, we said the wavefront is distorted, so there is a phase shift between different parts of the wavefront. Right, some parts of the wavefront are simply ahead in phase or delayed because of this different optical path lengths through the atmosphere. And if that wavefront error is less than 1 radian, meaning what's 1 radian is 67 degrees or something, degrees, meaning that one wave is shifted by 60 degrees in phase back with respect to the other. That's not that much. Of course, it has to be much less than 1 wavelength. But if it's less than 1 radian, then we consider the wavefront still as flat, and that defines then our free parameter. Analytically, you could calculate this parameter here. I'll show you some more inspiring pictures in that field. But you can, I think it's better to start with the definition up front. You can actually calculate it very precisely if you wouldn't have this structure constant of the atmosphere that we used before. And then if you plug in here the right numbers, then you will calculate what R naught is. What is important to take away from this formula is that this parameter, the value increases with wavelengths. You can see here R naught proportional to lambda to the 6/5 power. And it also decreases as the minus 3/5 power of the air mass. Because this one depends, if you go a couple of slides back, you can see that this one depends on the air mass. Okay, so what does it mean? Actually, it decreases with wavelengths and decreases with air mass. Well, if you that's not a good thing. Decreases with the minus power. So an easier way would be to say decreases with air mass, right? Sorry. So. Okay, that means that this free parameter shows us the size of the sky that gives us a flat wavefront. Ideally, we would like to have the whole sky be flat.
So R0 should be very small.
Ideally, R naught should be very big. And yeah,
if R is big, you can consider the whole wavefront to be flat at large scales. Like if it's small, then you only have patches that are flat.
Okay. So
yeah.
R0 should be large.
Yeah. I mean, to give a typical scale length at optical wavelengths, it's typically 20, 30 centimeters. And that shows the whole problem. If you have a big telescope, a telescope that's bigger than 30 centimeters, right, let's say this is your wavefront. Right? It should be, this is what it should be. And it's flat from here to here. So R0 is big, right? It's the whole distance. In this case, I could say, well, it's approximately flat from here to here, and it's approximately flat from here to here, and it's approximately flat from here to here. Okay? But not the whole way. Now my telescope, let's say it's big. This is my telescope here. And this is where the problem starts, because if this were the this is the ideal wavefront. And my telescope optics would then focus the light into one spot. Okay? This is the ideal case. And now, this is the turbulent wavefront. And the light from here actually is the mirror there. And it will make an image here. Now, unfortunately, my telescope mirror is bigger than R0, meaning that the light from that part above the telescope will actually travel this way. Yeah? And being focused here. So in the end, in principle, I have a couple of images from my star. One here, I can continue that. And unfortunately, this thing is also moving in time. So these things are moving around. And this is what you saw at the movie before. Right? So there's constant motion. And now if you had a telescope, now this was our big telescope. If you had a telescope that were smaller than R0, so if you had a telescope that had only that size, right? Typical backyard telescope of whatever, 8 inches or so.
Yeah, Raphael's telescope.
Sorry? Raphael's telescope, yeah. Okay. Then that telescope would only see that part and not know that much about turbulence. It would, the only effect, because you only have that one R0, one free parameter above your telescope, you would only see a sharp image, but moving around. And that would be the simple tilt component. So in principle, if Raphael could follow the sky and move the telescope very quickly, so millisecond scale, then he would still get a sharp image.
So far, it's only recommended.
Right.
But with the same frequency of the turbulence.
Yeah. Okay, so what this means, we want R0 to be large. The larger the better. And we see that it scales with wavelengths. That means that if you go to longer wavelengths, it increases. And that is simply that, how shall I say that? In simple words, longer wavelengths are more tolerant to wavefront errors. We see that all the time. I mean, if you polish a ultraviolet telescope, and look at the radio telescope, right? It doesn't matter if you walk around across it. James Bond has done it in movies. It's still a telescope. They wouldn't have allowed James Bond to walk on an optical telescope because the footprints destroy the image quality. And that's simply because the deflections, and it's now in the telescope mirror or in the atmosphere, if they're small compared to the wavelengths, they don't matter. Right? And this is seen in this formula here. If you go to longer wavelengths, the effective scale over which the wavefront can be considered flat is just bigger. At the same time, if you look through more atmosphere, you get more turbulence, and so it gets worse if you look at higher atmosphere. Okay, so we have this formula here that R naught depends on the wavelengths as to the 6/5 power, and we can determine then a parameter. This is very important. It's called the C, and that's simply sort of the size, the angular size. Right? We can, well, if you think back of the comparison of those two pictures, you could just fit, say, a Gaussian profile to any of the stars in the seen limited images, in the turbulent image, and you get an angular size, typically an arc second. Right? Arc second for a decent observatory. That's the size of your seen limited star. So, and that size is actually then given by wavelengths divided by this free parameter. So if you know the free parameter, you'll also know the C. Now we know, of course, that R naught depends on lambda to the 6/5 power. So now this is a very challenging math. Lambda divided by lambda to the 6/5, so you're left with lambda to the minus 1/5. Okay? And that means that the C, sort of the angular size of your scene, your blurred image of the star, will actually get better at longer wavelengths. So the worst scene is at optical wavelengths. If you go to the near infrared, the images get increasingly better with wavelengths. Okay? So you can then figure out what if you have, say, 10, 20, 30 centimeters at optical wavelengths, then this increases quite a bit, and then okay, according to the scaling law, you're seeing it better in the infrared. So here's another graph that may be a bit more sophisticated than what I've drawn here, but it's essentially the same.
It's the same.
Right. So you have the wavefront here, flat wavefront, and then you have the turbulent here and here, maybe some wind. And then you have, of course, structure in this wavefront. And again, a simple model to approximate that structure is to say, well, there is a zero order component, which is the tilt of the wavefront. This is the tilt component that gives you the tip-tilt image motion in the small telescope. Of course, it's also there at the large telescope, but it's not so, it gets less important there. But then there is also some fine structure, even for the tilted components, the roughness here, and that will give you many different speckles that will grow. So R naught essentially describes an average size. Of course, you can't go there and look at the atmosphere and say, oh, I can measure it with a ruler and it's 43.7 centimeters. It's a statistical quantity, essentially. You have a wavefront that looks like that, and then remember the definition was what's the average size scale over which we consider the wavefront error less than 1 radian, or any equivalent definition. So you always end up with a number that's sort of approximating a good quality wavefront. Of course, it does not have a really physical representation there, but it means that typically on size scales of a few tenths of centimeters, this is the scale. If you make it larger than that, if you make your telescope larger than that, then you get blurred images, you suffer from this turbulence. Okay? And then, as said before, each of those are knots. It's like here, and you have 2 images of the star here. And those images are called speckles. And each of these are knots, and that's a bit simplified picture, but produces a speckle. So actually you could see that. I should replay the movie because I think it's really best seen there. If you look here, so you see the tilt motion of the cloud, but you see also minus one star. These are not sunspots or so on the star. Remember, the star is not resolved. It should be just a point here. But the fact that you see here many points means that you have many speckles here. And in this simple picture, again, simplified, you could actually say, well, if this is an optical image and R naught is 10 centimeters, and I have at least 1, 2, 3, 4, 5, whatever, 6, 7, 8, 10, so I must have had at least a 1 meter telescope. Because across your 1 meter aperture, you have 10 different speckles, each one corresponding to one R naught, and maybe R naught is 10 centimeters. But that also shows you how complicated it gets now. If you build a 40-meter telescope, for example, the atmosphere is still the same. Right? But then you have 400 R naught across your aperture. And all of them give you some image of the star, and you need to correct for that.
So it also means that the most suitable size of the telescope depends on the height you are observing. I mean, if you have a very large telescope, you have to be very high, where R0 is also very, very large. And if you go down, for example, here in Colombia we have this problem. We need to decide which is the best size of our telescope. If we are working in a desert, which is at 600 meters, so we need to calculate the average R0 and see which is the best.
Exactly. Exactly. I mean, from those considerations, it's best to be on the highest mountaintop. The only problem is, and that's also, it's a practical problem, that also ESO, for example, has considered. It gets very expensive if you go up high. If you build it on 2,500 meters, I mean, these big things, these are challenging projects. Right? You need many brilliant minds to solve problems. And there are no brilliant minds at 5,000 meters altitude. You simply can't work there. Okay? And then that what's like you have to then trade on the advantage of better performance with the fact that it doesn't help you that you have a telescope that in principle would work if all these problems would be fixed and no one can fix them. Right? So that would mean that you have to sample everything and test at lower altitude and ship it, but maintenance is still a problem. It's always a trade-off between performance and practicality. Same as for the South Pole. Okay, so so what will happen for the long exposure is that in terms of mathematics, and this is relevant because we can use it to get better images by image processing. Let's say we don't need to understand really what this is, but all we need to know is that for a simple picture to describe a seeing limit in long exposure is to say, well, we have a intrinsic intensity distribution of the source. So this could be a delta function, and we convolve it with this case this is the transmission function of the system, which includes the seen component. And what we see then is the convolution of those components. What this transmission function here does, so that's just the mathematical term that describes the scene. But in a very simple way, what it means for the image essentially is we show here that as a modulation transfer function, and we'll get back to that tomorrow. The main thing is that you would have an image, a modulation transfer function like the solid line, if you were diffraction limited. And if you had a C, this resolution, the size of your image, would be smaller, will be larger, meaning that the image is smeared, meaning that it's spatially filtered. So essentially you have a loss of high spatial frequencies. I mean, I think what's this? We'll get, I realize this is maybe a bit out of context. It will hopefully become clearer tomorrow in the next lecture, and we'll ask about this then tomorrow in the test. But it's important to keep it in the record, because the angular resolution with the C is then back to a resolution of lambda wavelengths over the 3 parameter, rather than what you could achieve if you had a diffraction limited telescope, then the resolution would be lambda over E. And lots of high spatial frequencies means simply that, let's say you have a very close binary star. So you have a very tiny distance in between. Small distance means high spatial frequencies, and this will be lost. You cannot separate them. So in simple terms, you lose high spatial frequencies, and the resolution is degraded in the long exposures from lambda over E to lambda over R naught, where R naught is the free curve.
So it means that having a telescope, a 100-meter telescope, will be the same as having a 30-centimeter telescope.
If you do not correct for the C, the resolution is given by lambda over R naught. R naught is the property of the atmosphere. It does not care what size telescope you put behind it. Right? So, yes, the 100-meter telescope will not give you a better resolution than Raphael's telescope in Bogota if you don't correct for the C. Well, it will still collect more photons. So you will still have brighter images, but they have the same blurred structure as the small telescope. And this is the reason why all the big telescope projects, larger than 8 meters, essentially includes adaptive processes.
And that's why also astronomers are zero while the rest of the people working.
Yeah. Okay. There are 2 more aspects. One thing that we should consider, namely that that's also important when we do adaptive optics. When we discuss it later, so let's say there is a technique that measures the wavefront, corrects it, fine. But the problem is that the atmosphere is changing. Right? Because of the turbulence, it's not static. And it changes on timescales of a few tenths of milliseconds. And you can actually calculate it. This is called the atmospheric coherence time. So this is essentially time over which the image quality will stay constant, or the time over which there is not much change in the structure of our waveform. More quantitative, where the wavefront does not change again by more than 1 radian in phase. So this coherence time describes how fast the turbulence is. And when any system you build to correct for this turbulence, of course, has to be faster than that. And the other thing is the sort of the isoplanetic angle. And that's a very nasty thing. Because, let's say in the ideal case here, that we have our star is at infinity here, and we have a turbulent wavefront. telescope here. So this is at infinity. We have parallel light coming in here. And let's say, okay, doesn't matter. But let's say we have here above our telescope, we can measure that. Don't worry how we do this, but we measure this level. And we can correct it. And then we get a great image of that star. But who wants to stare all night on one star? So we may want to look at other objects as well. Right? Could be some galaxy here. The problem is, if I look at that part of the galaxy, I would have to look in this direction, right? Now I measured this part here of the wavefront. What I did not measure is this part here. So I will not correct for that. Obviously, if I measure my wavefront using a star here and look at an object here close to the horizon, whatever the atmosphere does here has nothing to do with what I measure here. So all these systems that correct the atmospheric turbulence only work over very small angles or a small field of view. Yeah? And that is given by this parameter here, the isoclimatic angle. And again, we see yeah, this is the, sorry, it's not theta, I think it's the Venus distance and our famous free parameter, and an average height for the turbulence.
And this is the average velocity of the turbulence, yeah, right?
Yes, the wind speed.
So if this is 1 meter per second, this RC is 0.3 meters, you have a 0.1 second.
Yes.
That would be very fast.
Yes. That's one of the reasons why people building adaptive optic systems for large telescopes are actually worried about computation speed, even including Moore's law. They say, okay, I only need it in 10 years, and I look at the processor speed now, and then even then, it's challenging, because you have to do all kinds of complex matrix inversions with or diagonalizations of matrices of 400 by 400 elements at 1 millisecond level.
Bernard, which is this cause this break that I don't remember its name.
I think that's the
yeah,
Siemens distance.
that's it.
That's only the Siemens angle.
Ah, okay.
Right, because again, everything gets more difficult when you get close to the horizon. That's one of the reasons why most modern telescopes only work to 60 degrees. I mean, of course, you can move them further, but okay. And now finally, we talked about speckles, so this should not be new to you. I just thought if I show many times the same thing again, it will become a bit more approachable. So, okay, we said you have a large telescope aperture. That means that there are many of these R0s above the telescope. So this is your telescope pupil here, and this is then the effective size over which we set the wavefront flatter than 1 radian. So and then all of those produce an image, and this image would be sort of a diffraction limited image, one speckle here, where the size of the speckled cloud is lambda over R0, right? The time average that will give us the C cloud. But there is information in each individual speckle. And so people say, oh, hold on, if I take short exposures, maybe I can preserve the information that's in each of those speckles. And the speckles tell us more about the object than the time average, because that is all washed out over time. And this is called speckle interferometry. And I'll show you a movie here. This is this is not adaptive optics. This is just taking series. Well, you calculated the coherence time. So obviously, I have to take exposures that are shorter than the coherence time. Well, at maximum that length. And if I do that, then during those time, I say the wavefront is constant. And then okay, this is the integration time, and that's shown here. So all of these images that you see here is essentially the image of the object. And you can see it's moving around, right? Remember the overall image motion, that's the tip tilt component, the overall tip of this wavefront. And you can also see how the amount of turbulence changes. I mean, now it's really bad, right? It's not constant. It's really, sometimes you get much worse, sometimes now it's getting better. The brighter the spots here are, that means the more light actually is in concentrated, and that probably is a sign. Oops. Okay, and what people do then is to use that information mathematically, and we don't have to go into how this is done, or this tomorrow. But to use the information with cross-correlation essentially of the various speckles in here and reconstruct an image. And what's shown on the right here is the reconstruction taking the information from all the images into account. So you have now, well, we are in frame number 120. Again, we don't co-add them simply, but a computer analyzes these images and then just adds the information from the individual images, not the images themselves. And then from the reconstruction, this is a pure computer algorithm now, from the reconstructions, you get this image. Right? And I think it's obvious what the game is, right? No one, if I show you that image, you would not have never guessed that it's a double star system.
To what extent does speculative geometry replaces adaptive optics?
Yeah, that's a good point. The problem is, if you remember, the exposures have to be shorter than the coherence time. And you need to be able to see the speckles. So the method is limited to objects that give you sufficient signal to noise in 100 milliseconds.
So we need very detectors.
Well, so imagine you would like to do, what you say, oh, I look at my gamma ray burst at redshift of whatever, 7 or something. Right? It's a faint object, and I want to see where it is in the galaxy. The problem is that you have to expose at maximum, say 100 milliseconds, and you will see nothing. So what's the computer going to do with that noisy image? It will not be able to reconstruct anything. And so this is very limited to bright objects.
You also need 400 times more storage in your computer to get all these 400 images.
Yes.
Who's not?